everybody, welcome to the Circus seminar. This is our third of 4. So today we have Professor Sara Beery, and next week, 2 weeks from now, we'll have Professor Dillahunt, so please mark your calendars for that last Circus seminar for this fall. So it's my pleasure to welcome Dr. Sara Beery, who is an assistant professor at MIT in the Faculty of Artificial Intelligence and Decision Making. Professor Beery was previously a visiting researcher at Google, working on large-scale urban forest monitoring as part of the Auto Arborist project. She received her PhD in computing and mathematical sciences from Caltech in 2022, where she was advised by Pietro Perona and awarded the Amori Doctoral Prize for her thesis. Professor Beery's research focuses on building computer vision methods that enable global-scale environmental and biodiversity monitoring across data modalities, tackling real-world challenges, including spatial and temporal domain shift to learning from imperfect data, fine-grained categories, and long-tail distributions. Professor Beery partners with industry, non-governmental organizations, and governmental agencies to deploy her methods in the wild worldwide. She works toward increasing the diversity and accessibility of academic research in AI through interdisciplinary capacity building and education, and has founded the AI for Conservation Slack community, which if anyone doesn't know about, now know about it. Sara also serves as the biodiversity community lead for Climate Change AI, another great thing to know about. And she founded and directs the summer workshop on computer vision methods for ecology. Could we all give Professor Beery a welcome?
All right. Can everyone hear me okay? Awesome.
A little louder?
A little louder. Okay, I'll do my best. Esther and I were talking about how both of us are not necessarily like innately loud speakers, so it actually does help to have the mic. Yeah, so I was really honored to be brought in to talk to this group. I think the work in Circus is really exceptional across a bunch of different, a bunch of different application domains and different fields. I mostly focus on specifically environmental and biodiversity monitoring, and my methods are pretty core in computer vision. So maybe there will be some intersections with some of the things that you guys are all thinking about, and maybe some things that are a bit different about this application domain. But today I wanted to share some recent work and some of the thoughts I've been having on kind of what our goals are when we're thinking about building systems or building tools that are actually usable and useful and can lead to impact in some of these very important application domains. And so to start off, just to motivate maybe sort of why I am so passionate about biodiversity monitoring, why I think this is maybe one of the more important or impactful or exciting areas to be working on, specifically with computer vision, we first have to reflect on the fact that we're currently facing what's called the 6th mass extinction. We're actually currently at a time when we are facing extinction rates across the taxonomic tree that are higher than the last extinction of the dinosaurs. So we are living through something that, if you ever learned about the different extinctions of the dinosaurs in school, it always sounded like this crazy catastrophic event. But actually, these extinction events happen over very long timescales. It's not always something that you can just immediately see this massive change. And it kind of does reflect on what it means to understand change when that change is happening slowly. And how do we determine what actually is necessary change, just innate fluctuations and change in the ecosystems around us, and what is change that we might actually want to try to address or to mitigate. And it turns out that, a huge factor in this biodiversity loss, at least according to ecologists and biologists, is linked to human destruction of habitat and the massive shrinking and fracturization of wildlife habitats globally. But also, another huge factor is climate change. And there's been some recent work that's discussing actually these intersections of human-wildlife conflict increasing specifically in areas that are also at most risk of climate change, often in the developing world. And it turns out that sort of linked with this sort of intersection of habitat loss and climate change and other, human factors, we've seen populations of wildlife go down by close to 70% globally. This is on average. These numbers actually are in the 90s when you look at certain parts of the world like Central America. And what this means is actually just the number of animals, the amount of wildlife from 1970 to today has gone down by 70%. So that's within probably some of the lifetimes of people in this room. And it's not just that the populations are shrinking, we're actually seeing extinction rates go up exponentially across the taxonomic tree. So not just mammals, birds, but also vertebrates, other vertebrates. We're really seeing this hockey stick effect. It probably looks like the hockey stick effect many of you have seen when we look at climate projection. And biodiversity is really not just valuable in and of itself. It's actually really intrinsically linked to a lot of things that are important to us as human society. Biodiversity is linked to climate change. Yes, there's definitely climate change effects on biodiversity, but increasingly we're understanding that biodiversity itself feeds back into that, that climate cycle, these ecosystems. It turns out one of the most valuable factors, or one of the most impactful factors of transferring forest carbon, which has a life cycle of around 100 years, into soil carbon, which has a life cycle of closer to 1,000 years, is bioturbation from small to even micro-scale organisms within the soil. Sorry, I should have turned on Do Not Disturb. The other really interesting factor is the effect on public health of shrinking biodiversity. We really have seen, as habitats shrink and as sort of humans and wildlife are interacting more and more at the boundaries of what used to be wilderness and human establishment, we're seeing increased risk of zoonotic disease spread, things like COVID. Food security is also really innately tied to biodiversity. I'm sure all of you have heard about the loss of pollinators and what a huge catastrophe that could be for global food sources. But not only do we rely on pollination, it actually turns out that the diversity of pollinators has a direct link to the nutrition in the food we eat. So it's not just a matter of saving one pollinator, it's actually important that we keep a diversity of pollinators. And finally, this is probably the thing that most people have maybe heard about in the past, is this thing called ecosystem services. Things like the urban forest, which explicitly provides air filtration, stormwater runoff mitigation, carbon capture, this incredible ecosystem of value to human life. So if you're not convinced that biodiversity has value in and of itself, it does actually really have value to human society. And I'm not the only person who thinks this, and I'm not the only person who's thus very concerned about the loss of biodiversity. But it turns out that one of the really big challenging factors here is that biodiversity is not something we can directly sense. So there is no such thing as a sensor you can go out and put in the world that will capture some explicit measure of biodiversity. Unlike something like monitoring weather, we can't just put out a temperature probe or a rain gauge and actually directly measure some component of a system we want to model. Instead, we can only implicitly measure it. And because of that, we've actually really seen this incredible diversity of sensing technology, everything from imaging systems at the macro to the micro scale, these complex things like this is it's what's called a moth trap. It's a light-based trap that captures moths and photographs them so you can identify moth diversity at night. Sonar systems for monitoring in areas where you can't actually get the visible spectra. Audio, hyperspectral satellite imagery, and then increasingly something we call community science or citizen science. This is actually relying on the human population as a sensing system. relying on human intelligence to actually go out and collect interesting data, and really the factor of scale that we get from the huge population of humans that actually do care about biodiversity and are interested in the natural world. And because of this, we have this incredible diversity and also incredible scale of data that's collected. We work with everything from satellite imagery to low-flying aircraft or drones, on animal sensors. These are things like collars, which you might have seen, that are actually tracking the movements of individual animals over very long time horizons, and increasingly have been used as actual animal-driven sensing technology. So, for example, underwater, where we still know very, very little, they're putting salinity sensors and temperature gauges on collars or on sensors they put on marine wildlife, and then they're actually building their models of change in ocean temperature with that information that's being collected by this intelligent sensor. Networks of stationary sensors, things like camera traps, bioacoustics, networks of sonar. These are sparse, of course. They're just sort of explicit points that are capturing information, but they have an incredible temporal longitude. And then community science, like I already addressed. And the scales of data that we're collecting across all of these sensors are pretty massive. So for example, in what's one of the largest curators of biodiversity data, GBIF, or the Global Biodiversity Information Facility, there are now close to 3.2 billion records of species occurrence. And these are coming from an incredible diversity of sensing technologies. But one of the challenges is that sampling bias on any of these modalities of data is not uniform. And almost every modality has some species that it's better at capturing than others. And in some ways, it's actually, some of the sensing technologies have been designed for this. So this is a camera trap that I put out in the savannah. You can see the elephants I might want to take photos of are actually behind the camera. This is one of the limitations of this ground level sensing, is that it has a limited scope, limited field of view. But also the actual motion triggers themselves on something like a camera trap are really built for warm-blooded animals. So if you're using something like an infrared-based trigger to capture data, you can see that you're going to have this really explicit bias towards warm-blooded species over cold-blooded ones, which means you're going to be potentially missing a lot of cold-blooded reptiles or amphibians. And this is just one illustrative example to talk about kind of the limitations and the complexity of trying to bring together data across lots of different sensing platforms that have their own implicit biases, both in terms of where we put the sensors, but actually also in terms of what they capture. And so if we think about looking at just a couple of these and actually zooming out, now not even looking at what are they good at capturing, because, for example, humans are really great at capturing things that humans think are interesting. So we have a huge bias towards plants when they're flowering because people like flowers. And we have very, very little data coming from community science platforms of just things like native grass. Because when's the last time you stopped and were like, yeah, I'd really love to take a picture of this grass? And now, of course, there's a few passionate weirdos out there who really love grass, and they're like wholeheartedly sticking with it and collecting information. But it's fewer and further between. You also get the same thing with things like slime mold, stuff that humans think is a little gross. But so if you just look at community science data, and you look at, this is a rough heat map, this is coming from my naturalist, of the distribution of where community science data is captured, you can see that there are some pretty specific patterns. And one of the biggest ones is people tend to take data where people live, right? And so, and increasingly, not just where people live, but where people live that are likely to have a smartphone with access to the internet, the ability to take high quality photos and upload them, and where people speak English, right? And iNaturalist is increasingly translated into many other languages, but this is still a limiting factor. You can really see there's a very large sort of Western world bias to this data. If you look at something like camera traps, now these are sensors put out in networks that are often put out by a scientist for the explicit purpose of measuring biodiversity and monitoring it. And they take, I would say sometimes lower quality data, but the nice thing is they can potentially be a bit less spatially biased. It turns out there still is some spatial bias here, but now it's spatial bias in terms of where can people who do science easily do science and what are their interests. And one of the things that's not captured, this is coming from Wildlife Insights, which is one of the largest curators of camera trap data. What's not captured here is who put out the sensor and for what purpose. Because often these sensors that are placed, for example, in East Africa, are being placed there by universities like Harvard or MIT or Princeton, as opposed to being placed by local scientists. And so then where the data goes is another question. But you can see that this has a very different bias than the human bias that's captured by a naturalist. And then, you could scale up to something like global satellite imagery. Now, this is something that does not necessarily have a huge spatial bias. So, of course, there's spatial bias in terms of where we have access to what types of resolution of aerial data. For example, NAPE is a pretty amazing platform for higher resolution data in the continental US, but it isn't necessarily accessible other places on Earth. But here, the bias you have is what you can see. Because it turns out that while there's incredible depth of information coming from some of these new platforms and different hyperspectral sensing, there's still a lot that actually cannot be seen from the air. And not only can things maybe not be seen from the air, we see that for specific types of tasks, particularly even when you're talking about things like trees, which are very large and don't move, so you'd think that there's this like long-term spatial revisit and you could actually get pretty reasonable accuracy, that if you go to ground level imagery, your accuracy can sometimes double or even triple versus trying to do space-based identification of species of trees at the individual tree level. Now, a lot of these things are constantly growing and increasing, and maybe we'll get to a point at some point where we have this really nice intersection and we're getting more and more high resolution data from the air and more spatial coverage from the ground, and we're really able to kind of meet in the middle. And that's kind of where we're hoping to go. But we still, in the meantime, need to figure out how to model and how to work with the data that we do have, which you can see is pretty biased, but biased differently for different types of data. And also really sampled heterogeneously. So when people talk about multimodal sensing platforms or multimodal systems in computer vision traditionally, they're often talking about data that's already co-registered. For example, an image with an associated caption or video with audio, but they're actually captured at the same place and time, as opposed to thinking about dealing with multimodality that has this heterogeneous sampling strategy, where now you have to figure out how information should flow across those modalities and in what way. And really just, again, scaling out. This is true for many things we might want to study, but I think especially true for biodiversity. So this is, again, these like 3 billion species occurrence records in GBIF. You can see there's a pretty big bias, again, towards the Western world. This is an estimate of alpha diversity, which is the simplest possible sort of scalar metric of diversity. It's just an estimate of the number of unique species that exist in any given place. And you can see that these are almost anti-correlated. So we possibly have the least amount of data where we need it most if we want to think about how to mitigate biodiversity loss and where that might be most impactful. But this lack of IID-ness in the data, and also the fact that not only is the data sort of spatially sampled over time, not IID, but actually the underlying system we're trying to capture is not something that is static. Species distributions change constantly. Migration is a huge factor here, but also overall species ranges are changing year to year, and that's happening faster and faster with climate change. There's no such thing as a perfectly independently and identically distributed set of information that you can capture, where then you can build a machine learning model that sits in this IID space. We have to build things that can change and adapt and move out of distribution. And this is something that violates a lot of the fundamental assumptions we make about machine learning, right? We start from assume that your training and test data is IID. It's not. It's not here. It never will be. So we have to figure out how to work around that. And it turns out that this lack of IID is pretty universal in biodiversity and in ecological systems. So this is 100 million trees in the Neon Crowns data set from NEON is the National Ecological Observatory Network in the US. It's a bunch of different sites from across the sort of different ecosystems we might be interested in. And here you can see that not only are the distribution of species changing, but also just the density of trees. And one of the things that they've really found is that if you try to build a model across some whole set of ecosystems and move to an ecosystem that hadn't been seen before, that's out of distribution, performance really degrades. Similarly, if we're looking at something like trying to detect and count salmon in static sonar, this is for trying to maintain sustainable fisheries across the Pacific Northwest. You can see that as you move to a new river, there's a bunch of things that, again, move you out of distribution. Different species, different sizes of fish based on the sort of dimensions of the river, the bathymetry of the river gives different reflectance. And again, we need something that can change and adapt out of distribution. And similarly, if we're looking at, acoustic sensing, so this is one sensor here. You can listen. So you can hear both different species calling, but also this kind of specific background signature. And if we move to another sensor and listen to those same species, you can see how the background signal can really vary. And in this case, we're not even talking about out of distribution in terms of like moving to a new ecosystem, to a new part of the world. We're literally just talking about moving from one side to the other side of a very, very small but protected park. And so, again, we really need to build models, potentially, that are generalizable, and that can adapt to different sensing in the background, can adapt to different contexts, can adapt to changes in distribution, but fitting with sort of the historical way that we try to think about this in computer vision, there's a lot of focus on building one model that will work as well as possible everywhere on Earth and will sort of work equally well, in some sense of the word equal, for either of these sensors, for any sort of the different rivers in the Pacific Northwest, for example. And it turns out this type of distribution shift is really not specific to ecology. It's actually just a function of the real world. There's basically, I have never come across an application in the real world that does not have this sense of distribution shift. And working with an amazing group of researchers, we really tried to push the machine learning community to deal with the types of distribution shift that we do see in the real world. Everything from moving from one hospital to another, to one camera trap location to another, moving across countries, across time, across users on Amazon, et cetera, et cetera, et cetera. And the list of sort of benchmarks that are capturing this real-world distribution shift within the wilds data set continues to grow. And one of the most, I think, interesting factors here is that if you know that you have a system that needs to generalize out of distribution, I think we need to move away from the idea of testing that system in distribution. We really want to have a good sense of what performance might be out of distribution. So you should split up your test set and actually capture some realistic testing scenario. But there's another challenge here, which is that you can get a number on this. That number will not necessarily be generalizable either, right? What you've tested is distribution, generalization to one very specific held out fixed test set. But actually, if you want to deploy these things in the real world, you need to constantly be reevaluating because these models the performance of the models changes as the distribution changes. And I think one of the more important things is if we want to understand, using our systems and our models, what the underlying ecosystem change is, then we must be able to disentangle how model performance is changing as the ecosystem changes, despite the fact that those two things are correlated, which makes it kind of challenging. But one of the most ubiquitous things we see is that performance from in distribution to out of distribution degrades significantly. And another really interesting thing that I think is something that we shouldn't ignore, Ludwig Schmidt at the University of Washington has shown that even in these cases where we're trying to build models that generalize out of distribution, now, while we might not be able to say anything about what the actual performance out of distribution will be without some sort of efficient evaluation, that often the best model in distribution will be the best model out of distribution, which is interesting, right? It seems to suggest that if we just do our very best on some in-distribution case, that still will be potentially the best model to use out of distribution, assuming a bunch of things like, oh, the categories stay reasonably the same and whatever. But what we can't guarantee is how good it will be, or whether it will be good enough to be useful, which I think is a really important piece of the puzzle. And we really find that this degradation, as you move out of distribution, this isn't just like a species rarity thing, because the other factor here is a lot of these things are long-tailed. There's a lot of things that are very rare. We know machine learning models really struggle to recognize things that are rare. But it turns out it's not just the things that have fewer training examples that struggle to generalize. That generalization gap continues, even when you have species with lots of training examples, 10 to the fourth or more. And part of that, we think, is due to the differences in distribution at, for example, for static sensors, individual sensor locations. And this is just looking at the per category distribution of species of interest. This is what is often referred to as subpopulation shift. The species you're interested in maybe stay the same, but the amount of them at different places or at different times change. Very reflective of something like migration, of course, right? Because you're going to have fewer of a species and then more of a species over time. It turns out that if you already know the distribution, assume you have some oracle or maybe a very good expert that can model that distribution, you can take a really simple Bayesian step over the output likelihoods of your predictor and improve performance sometimes by 10, 15, 20%. But this, of course, assumes that you know the distribution that you're going to have, which we don't know. And distribution testing is a very, very challenging statistical field, even when you do have IID data. But this actually gets at another interesting thing when we're thinking about usefulness, which is in what ways can we reduce that subpopulation shift? And one of the kind of, let's see if this will actually play. One of the hackiest things you can do to reduce subpopulation shift is just map everything up the taxonomic tree until you just have one category of things you're interested in, which is animal. And while this is not actually solving anyone's problem end to end, because biologists need to actually understand what the distribution of species there are, it turns out that if some of these sensing technologies were capturing 70, 80% of the data, which is empty, and so just having a very good, very generalizable, off-the-shelf thing that can just filter out the empty data and works on species and on ecosystems that were not seen during training is incredibly useful. So this model gets used 43 countries, thousands of different projects, researchers worldwide. It's not fancy. It's just a class-agnostic object detector. But the interesting research here that led to the the development of this useful model was exploring the trade-off between generalization and specialization and sort of taxonomic granularity, and determining that actually the most useful thing might be the thing where we don't ask it to do the hard thing, which is identify species. Yeah?
Identifies moving objects. This is what it does.
So it's frame-wise. It turns out that there's a lot of classic movement detection stuff. It tends to fall apart in camera trap data specifically because the frame rate is very low. So you triggers and you get one frame and it's kind of variable, or it'll take a set of frames, but it's one frame per second. So stuff like optical flow and even the pixel distances are changing quite a lot. So classical methods don't tend to work very well for motion, but this is just per frame, find me animals. And we do actually do humans, animals, and vehicles are sort of the set of coarse granularity classes for this model.
Leading data of animals came from
ecologists. Yeah, lots and lots of ecologists. We talked to the community, brought together a huge amount of training data. The bounding box labels were paid for by Microsoft. But this was back in 2018. And it still is one of the most widely used, I think, models for ecology out there. Really just speaks to changing the way we think about what is useful and what is needed in these real world scenarios. Yeah, you had a question?
Is the intent of this research to analyze single mode, single discipline topics and then integrate them? Or is it to integrate or generalize the representation into a single model that includes the diversity?
Actually, I mean, I think my research is somewhat trying to determine, of those two modes, when should we do one and when should we do the other,
I see.
right? And in what cases are each of those different modes effective and usable? Because I really want to move us away from this kind of traditional machine learning centric space where we come in and we say, oh, well, machine learning could solve your problem, and we train some model, IID, and we get 99% accuracy, and we're like, great, we've solved it. We've solved biodiversity monitoring. But sometimes general representations are useful.
If you think you've solved the problem with that rather narrow data, is the problem?
Yeah, I think so. Yeah, and I often get very suspicious, actually, and I think all of you should, when you see numbers in the 90s for real world problems, because it turns out that machine learning is getting better, and particularly GPT-4, really amazing, actually, truly amazing at capturing things that are of interest to humans selling stuff on the internet, but it is really, really struggles with stuff that is less sort of common knowledge, is what we've found. And so there's still room to grow, and there's still room to improve. And this is just an example. Actually, this is really fun. I put this in a slide for a talk I was giving at University of Idaho like about a week or so ago. And this person was in the crowd. I had never actually thanked her, and she came up. She was like, "That was my tweet." But this is someone from the Washington Department of Fish and Game who used this model. This is just one camera. She found the one animal in 170,000 images of blowing grass. And then from her perspective, now she's like, okay, that's a bird. Cool, it's a bird that we're not even studying, so I don't really care, but it saved her a ton of time. And that's something I really want to think more about, is how do we actually build things that are usable and save time? And I think when just sort of talking to what the gentleman in the back brought up, it turns out that you actually can try to think about building useful global representations without expensive labels if you already have the global data in hand. So I think particularly for things like satellite imagery, remote sensing imagery, where we actually have the data already from the entire sort of representation. Now, of course, things are changing over time, year to year, but we have this global set of data. We might not have global labels, but you can build something where you have an in-distribution representation. And Esther has some really amazing work called Mosaics that I think also gets at this. Building representations that can be really easily and efficiently adapted to specific downstream tasks, but where the representations themselves are built or learned on the entire distribution of the data. This is not something that we have necessarily from community science data or camera trap data. And so now you need to try to figure out if the representation you built on the data you did have in hand does actually sort of capture this out of distribution scenario. And one of the things now, if we're moving to a place where we don't necessarily have data everywhere, that we've been exploring is, when do you actually get better by including more data? So if I'm trying to build a model of urban forests, this is a project I did in my postdoc at Google, and you want to build something that is sort of general. You want to build your best possible sort of comprehensive model, and you have maybe capacity to train on a lot of stuff, then you might just train on 9 million images across 23 different cities, and then test on all of those cities. And you use a lot of training budget that way, but maybe you have it if you're Google. And so here what we're looking at is, if we go per city and we look at training on just the set of data for that city, which of course is a lot less training data. We don't have the numbers on here, but on the order of usually somewhere between 50 and maybe like 400,000 training examples across the entire category set. That might sound like a lot of data. In computer vision, it's not that much data. To training on the regions, this is sort of the red being the west, the blue being central, green being east, the sort of regional distribution of data, versus training on that entire comprehensive data set across the whole of North America. A lot of times you do see like nice kind of gains. So like in Seattle, for example, you kind of consistently see improvements. You can also see there's diminishing returns. So you're not getting often way more performance by training on global data versus regional. But then in some cases, like Los Angeles, you actually really just don't improve your performance that much, going from 400,000 LA training examples to the 9 million training examples across the US. And now if you actually think about resources, about who's training the model and for what purpose, training on 400,000 images and hyperparameter tuning on 400,000 images versus training on 9 million is a huge difference in resource allocation. And we need to have a better sense. We need to have a better understanding of when it's actually going to be worth it for a given end user to include data from all over the world. When is it actually helping? And I don't think we have a good sense of that yet. But one thing, yeah.
So in the previous slide, the evaluation is local, right? That's
Yeah, evaluation is local. Yeah, and it's not IID. So we've split up each city into like sort of training and test regions. Mostly because we found that there's all this bias that comes into how people plant trees in cities. So we plant like all the same species along the same street. And so if you randomly sample, you get, again, like very, very high accuracy, but potentially not generalizable. So we're really trying to capture some sense of that. So training and then held out area, usually split up by longitude or latitude. And then these three with the asterisks, including Boulder, where Esther is going to be, where Jessica's from, those are actually completely held out during training. So these are kind of like totally unseen, test-only cities, just again trying to get at some of that generalizability. Okay. And these cases, the training, the in-city training is the very nearby, like Denver. For Santa Monica, it's LA. And for Pittsburgh, I think it was, I forget. Maybe, I don't remember. My US geography on the East Coast is actually pretty bad. Yeah.
And I think she can answer first.
Yeah.
I just wanted to say that we developed a method that actually, unsupervised method that would actually be really good at telling you which cities to train in order to improve your prediction.
Yeah, and yeah, I mean, I haven't covered it in this talk, but there's a bunch of really cool work in data attribution and trying to explore like when and how we might expect things to improve for what stuff. And yeah, I mean, I would love to hear about that specific method afterwards. Yeah. Yeah.
And maybe follow up after.
Yeah, that'd be cool. And this is sort of a more universal problem, right? It's not just specific to trees. I mean, we'd love to know when it actually is worth it to share data and when it isn't. And particularly as we move into these spaces where we're thinking about ownership of data, like understanding how and when and why it's kind of like worth it for you or worth it for others to include data in training and for what purpose, I think is a really broader and very important question. Yeah.
Yeah, so my other question was related to that. Is there some intuition of the cases in which you benefit from training on external data? Like, is there something about the similarity of the point versus its region?
So this is just like this is like a first order thing, but one of the things that seems clearly true is that this is just the L1 distance between the distributions. This is like that subpopulation distribution we talked about earlier, normalized, and so lower is close, like darker is closer here. You can see there's kind of these regional blocks that start to form. And if you just look at now the generalizability from one city to another, now lighter is better because it's an accuracy metric. But you can see that really there is some similarity here. And there's, at a very first order, just the difference in distribution, I think, is a huge factor. because these models are learning likelihood predictors, right? And so particularly in cases where they're confused, they tend to guess the more common species, which might actually be the thing we explicitly don't want if we care about endangered species. Now, of course, there's a lot of factors that come into play, like the long-tailed distribution and visual similarity across species, this very fine-grained categorization that I think doesn't necessarily occur as much when you're talking about categories in something like ImageNet. And even people will say like, oh, we're gonna do fine-grained classification on dog breeds. Dog breeds don't look the same. They really look actually very different, many of them. The number of sort of dog breeds that really look the same are very small, but the number of trees that look the same is quite large. Tree species ID is hard even for experts. Yeah.
I mean, you mentioned this a little bit earlier in your talk, that this seems like a case where like human knowledge could really help you. And
Yeah.
Yeah, we know that these are regions, and some things are close to each other but not similar, and we know this because we've lived here. And so I'm wondering, like, what's like the value of like doing it in this way where you assume you know nothing about cities versus like, let's build in all these assumptions that we know because we're people and we know things about the world. Like I can see that there's
Yeah, I'm not saying this is the best way to do it. This is like trying to benchmark what's possible if you don't incorporate any other knowledge, right? But I absolutely think that knowledge, or actually even trying to build in structure around like where and when species are likely to occur, where they thrive, like that's really valuable. And I'll bring up some work actually in a couple slides doing this sort of across the taxonomic tree. I actually think that really annoyingly, like street trees are one of the worst for this because people plant whatever they want and then they do stuff to manage them so that they stay alive. So there's like palm trees in Seattle. They would never sort of naturally occurred there. And so the sort of environmental covariates and the relationship with the species that exist tend to break down in cities. Also, in the natural world, we tend to have somewhere between like 5 and 20 species, like common species in any given forest. It's the diversity is not that large, but like San Francisco has like 400 genera of trees alone, like not even at the species level. So yeah, it turns out street trees is maybe like a weird one in this case. But this knowledge, trying to figure out how to capture knowledge from a community, or even from sort of all of the history of ecology and science that we're currently ignoring when we're just sort of training models on images, I think is one of the limitations of a lot of this work, and something that we will only do better if we're able to incorporate that information. So just in the last like 15 minutes or so, I kind of want to come back to this broader question, which is like talking about general models, one model that knows all the species of trees on Earth, or all the species of birds on Earth, or all the, who knows, a model that knows everything. And really reflect on when do we need a model that knows everything. So one case is when you're predicting on everything. If you as a user are doing global scale monitoring, if you are as a user actually capturing something sort of at this global scale, then you need something that can predict at global scale. This happens a lot in benchmarks. It often happens much less frequently in practice. So for example, talking to Hannah Kerner, who's one of the people who built that Presto model, this kind of generalizable starting representation. Now that's just a starting point, but actually what they need are often country or region specific models. And in order to get the accuracies they actually need to be able to inform a decision maker, they only trust models that are region specific and time specific. They'll build a model for last year or for this year for Kenya. And then they work with experts to incorporate more and more of this understanding from the community to be able to get to something that people actually can rely on and trust, and that they rely on and trust enough to actually make a decision on it. And these models are almost always specialized to a given place. And this is, but you know, in Kenya, I don't need to identify bobcats, and in Idaho, I don't need to identify giraffes. And these concepts are taking up capacity in a system, right? A lepidopterist doesn't need to know anything about sharks, and a shark biologist doesn't need to ID moths. And so it kind of begs the question of like, when do we actually want systems that know everything, and when do we not? And again, this is another example, but Ben Weinstein, who did that work with neon trees, here they're looking at using hyperspectral data to get actual like individual species ID across these neon sites. And their best results, the results that the neon sites are actually happy to work with, are they build this ensemble of specialists. They build a model for every year, for every taxonomic group, for every location. And then they ensemble all of these sort of year, location, taxonomic group experts into some prediction. And that, for them, works much better than a model that actually needs to work and understand and capture sort of all of these things at all of these times. And they have no expectation that this will generalize to future years. They plan to build new models with new data each year, because what they've recognized is basically they need some amount of useful overfitting to be able to get the accuracies that they require. And this, you know, yeah.
Do you have any intuition on why it's useful to do per year and not per season or something else?
Because they're incorporating temporal, they basically incorporate some amount of aggregation over time. And the different trees have different sort of, each year they, what's the phylogeny? The phenology, that's the word I'm looking for, not phylogeny. The phenology of trees, or sort of when they flower, when they use their leaves, like that changes year to year. And my intuition, at least, of what Ben has told me, is that that is so different year to year, and like when they capture the data and sort of in what ways are so different year to year, that maybe they just don't yet have enough years to kind of learn to be invariant to those things in a way that's useful. Yeah.
I do research in knowledge representation, and I'm trying to imagine what a generalized model is.
Yeah.
Is it merely, I don't mean merely, is it an ensemble of heterogeneous models with links that allow you to follow the link to the additional causal factor?
I think that's one way that you could try to represent that, but I mean, I'm not actually sure what the best general model is. And
You're talking about generalized models here. Do you have a range of what those models actually look like?
I mean, I guess it often what you want to generalize over, or like what would be important to generalize over, is dependent on.
I mean, generalize down to like your example of multiple animals down to a single animal?
Sure. Yeah. I mean, I'm happy to talk more about this offline, but basically, like, I think that I'm not sure that I have a good definition in my own head for like what a universal model would be, and even whether that's something that we want. But in this case, it's not a general model. They're building a model for the neon sites, for the years they have data, for the species they're interested in. It's very explicitly specialized, and they really do not expect it to generalize at all. But it's useful enough that they're using it.
Do you have any impression or intuition about the knowledge loss or unavailable as a consequence of the lack of a generalized model?
Or I guess the flip side of that is when we try to build these generalized models, are we actually losing knowledge in the pursuit of generality? And I think a bit of both, maybe. So there's a caveat. It is way easier to maintain one model than to build a model for every single ecologist. From an engineering perspective, that's pretty intractable. And so it depends on who is training the models. And this is actually one of the reasons that I keep pushing for more capacity building in ecology. I want ecologists to be able to be good applied machine learning researchers and train their own benchmarks, because we're never going to have computer scientists who have the time and the capacity to actually train the specialized models that are going to perform best for these specific tasks for every possible task. But if you do only want to build one model, so for example, you're iNaturalist, right? You're the actual curator of all of this community science data across the board. This is some amazing work from some friends of mine, Elijah Cole and his collaborators. But you can actually build spatial representations of species. you actually can learn to model based on, and they use environmental covariates, but actually they find one of the biggest factors is just in iNaturalist, the species co-occurrence, which species are showing up with which other species. That's the spatial and temporal proximity of that. And they actually just build models of sort of the likelihood of any given species given a place and time. And then you can use these models to take that simple Bayesian step we talked about before to try to reshift the likelihoods of predicting anything. And in particular, they sort of evaluate these across a bunch of different downstream tasks. I really like the benchmark they built because they're looking at both predicting species presence, looking at the range. They use these as these geographic priors on image classification. And they actually regress specifically spatial features, these like geospatial features. And one of the things that they see in terms of like true positives versus false positives, true negatives versus false negatives, is that as they're increasing the number of positive examples per class, so as you sort of have more occurrence information, you're going from rare to less rare, you do get really much more increased, let's say, accuracy. So we still are really not seeing great performance for rare species, but they've found that in this sort of species co-occurrence framework, they do a lot better for rare species than if they try to actually learn each species in a vacuum. So there's information that's shared between common species and rare ones. So just blazing through at the end, what if you have resource constraints? What if you actually can't train a vision transformer? You don't have enough data, you don't have the compute. These large backbones can be expensive to fine-tune and to use. And most of the stakeholders I work with don't have access, even to GPUs, or bandwidth to move data from the field to the cloud. If you're talking about large images, that's a huge amount of bandwidth. The way we actually get data from our deployments in East Africa is we ship it on hard drives. That's still the fastest way to get the data. And if you need real-time information, you can definitely believe that this isn't tractable, particularly, things like camera traps. So recently, I've been working with some amazing researchers in compression, Dan Alistair being one of the leaders of this at IST Austria. And we've been looking at, if you have a large, accurate generalist model, can you very efficiently compress and specialize it to your task of interest and get a sparse specialist model? And basically, how do you best sort of make use of the fact that you might not need all of the capacity in the model, you might not need it to understand everything, you only need to understand the things you care about. And we do this, I call it TACO, which is very cute. But basically, it's a method that takes in sort of a model, a compression constraint, some sparsity solver, and some set of calibration data, and that calibration data is capturing your sort of task of interest. And just in particular, some of the kind of methodological novelty that we brought in. So looking at existing sparsity solvers, there's this optimal brain compression, very accurate. It eliminates weights in an optimal order, particularly, and then updates remaining weights. So you're doing this compression sort of optimally. And then there's this sparse GPT proposed basically what they call fast optimal brain compression, where they just have a very specific fixed set of removals, and then update remaining weights. This is accurate and slow. That's much less accurate, but very fast. We just proposed a hybrid that's accurate and kind of in between, where we use fast OVC for the really big layers. So things that have a huge input, they like sort of convolutional things that have tons of different channels. There we use the fast compression, and then for everything else we use the optimal compression. And so this takes about 90 minutes for a set of data. For a given model, this might take 4. Ours takes like 20, but on a CPU. Assuming you can fit it in memory, you can do that in 20 minutes on a CPU. And then sort of what we actually see is that going from sort of standard post-training compression to our specialist compression, we get the same accuracy with much higher compression rates when we're specializing at the expense of that upstream general task, right? So we get worse at sort of the general set of things, which is fine. We don't care about a bunch of stuff. But we are able to compress models to much smaller and maintain those same sets of accuracy. This is just comparing with just actually doing compression with our thing directly or doing fine-tuning of the final layer. And this is true across a bunch of different potential subtasks. And we can get basically 80 to 85% sparsity with almost no drop in accuracy. So if you need to run this on your laptop in the field, this is a huge boost. And it doesn't require like a ton of capacity to retrain or to actually run. And then we add this additional sort of distillation tuning where we can further improve accuracy, again, without sacrificing sparsity. The goal here is basically it's pretty standard, but you kind of have like an expert, which is the big model, and you just use an L2 loss and try to enforce that the representations of all the layers are the same for your small and your big model, or as close as possible in L2 space. And we get notable CPU speedups versus accuracy on a ResNet 50. So the nice thing here is that we're moving towards something where I can maybe actually deploy these things in the field on a laptop. And I think I've been thinking more and more as we have bigger and better general models, and these models are really getting bigger and better all the time. In a changing world full of very diverse tasks and unequal access to resources, should we increase our focus on efficient specialization as opposed to increasing our focus on sort of inefficient generalization? Kind of just food for thought. So thank you. We're really at time.